Hello again and welcome back to my channel. Today we'll talk about Segment Anything model, also called SAM. And this is the plan for today. So I'll start with the segmentation task itself. So on my channel I have a lot of videos about image classification models like ResNet, VIT, Swing Transformer, about object detection models like Detector, Dino, and so on. And this is actually the first one about the actual segmentation task. And I want to spend a moment to just explain the motivation about why I think this task is really interesting and useful for the future. Then we'll discuss what problem exactly does SAM solve, what is promptable segmentation, that is like a subset of different segmentation tasks that you can imagine. Then we'll talk about SAM's data engine, meaning that we'll discuss how they solve the problem of collecting a lot of diverse high-quality data, which is the main problem for segmentation tasks. Finally, we will dig into the actual model architecture, so if this tiny picture in the paper is not enough for you, I'll explain it in a lot more detail, and even if that is not enough, my next video, as usual, will be about reading the actual SAM source code. Finally, we'll discuss some results and applications of the model. So let's discuss segmentation task and why I think it is interesting. So coming a little back, this is an example of image classification task. That is, given an image, output just one class, in this case Beehive. And this is the task that is solved with models like ResNet, VIT, Swing Transformer that are also used as backbones for all the other models. This is an example of object detection. Now we have a picture, and in that picture we might have many objects. We might have just one object, we might have no objects at all, and then for each object in the picture we want to predict the actual class and the bounding box. But I want to stress that the actual difficulty with object detection is that the model always outputs fixed size tensor, and having variable number of objects in the picture, it's not obvious how to connect that to model output, and this is the primary problem that all of those models like Detector and Dino solve, on how to match model prediction with the ground truth, how to make it stable, how to make it train well, and so on and so forth. Once that is done, you can go from bounding box prediction to something like pose estimation really quickly. You just replace the head that outputs 4 numbers for bounding box coordinates with a head that outputs more numbers for different points in a pose, and you might use that for sport analytics or something like that. So this is an actual example of where it's quite often used for drawing something silly in a video or in a picture. So how this thing works is basically detects a head and then predicts some key points on a head like nose, ears, mouth, and so on. And then from the coordinates of these points, it estimates the actual 3D position of your head and then just draws something on top of that. And as you can see, it works quite well. So it reacts to my movements and so on. And of course, you're not really limited to that. You might swap that still for something like regression to predict object weights or calories, for example. And this is what segmentation is supposed to be doing. So this particular picture illustrates an example of instance segmentation. That is, we not only annotate each pixel to the class, we also say to which object it belongs. And we need to differentiate between different objects of the same class. So this shape is not the same as this shape. But once again, this is just the beginning, right? So the actual core problem of that is have this pixel-wise output. And once you have that, you can then use it for something much more interesting, like depth estimation. This is currently used in different autopilots, where you actually can reconstruct 3D map of the space just from looking at the camera, just from looking at the video preferably. And so here's an example of Andrej Karpathy from Tesla talking about how they reconstruct such a 3D map of environment from one camera or several cameras. Here's another example of video from Tesla Optimus bot, and we can see that it basically does segmentation in its vision task, so it knows that this is one object, this is another object, and in addition to that, what they do is they perform what is called occupancy detection to simply know which parts of space are occupied by some sort of object and which are free. So this task of pixel segmentation, of course, is more back to earth. It's simpler than what we've talked about, like occupancy detection or depth estimation, but it is a foundation for these tasks. And so it's really important for the future of AI, robotics, AR, and so on. And so that's why I consider it interesting. And the core challenges with the task is basically collecting ground truth data. So compared to bounding box, for example, to actually create annotation for one object for instance segmentation, that's quite a laborious task of annotating the pixels. So the way it's usually done is there's some sort of first estimation of a detector that provides some first estimate of segmentation. And then there are people who annotate that by hand by basically erasing incorrect pixels, adding missing pixels, and that takes a lot of time. In addition to that, with tasks like annotating an image with a text, you will find a lot of examples on the internet because people like to put images on the internet and then write something down there. So they do that on Facebook, they do that on their website and so on. You don't really find segmentation examples on the internet. No one enjoys putting a picture and then below an actual array of coordinates of pixels that belong to a certain object. So this is virtually unavailable on the internet unless you actually pay the cost of collecting the data yourself. And another problem that is discussed in SAM paper, and one with which SAM has to deal with, is that sometimes it's ambiguous. So having a point somewhere, it's not really clear where that point belongs to. So an example might be that it belongs to an object, it belongs to a part of the object, or maybe a subpart, and you need to deal with those details because it affects the benchmarks, it affects the usefulness of your model, and thankfully SAM does that. Okay, so what is promptable segmentation? Coming back a little bit, so this is the example of instance segmentation. So having a picture, we need to annotate every object in the picture. We need to say where each pixel belongs. And in addition to that, we need to predict the actual class labels and instance ID. So we need to say that this shape is different from this shape. One of the goals behind SAM was to build what is called a foundational model that is not just solving one task on one dataset or one challenge. It can actually be used in lots and lots of different places. And instance segmentation is not really good for that. So for one, it relies on a certain definition of what is an object and what isn't. So in this picture, that's a picture from Coco dataset, they have only 80 classes. So it does say, for example, that a dog or a human is an object, but not the gate here, for example, or the wheel. So depending on what your actual task will be, you might not be interested in that. You might need a different set of classes, for example. So what SAM does is it solves the task that is called promptable segmentation. And so promptable segmentation basically says that, having a picture and a point somewhere on that picture, let's segment the object to which this point belongs. So in this case, this point belongs to the person, and so we need to output the mask for the person. Another way to prompt it is with the bounding box. So we can say that this is our prompt. Please output us the segmentation of the object that best matches this bounding box. And so one of the reasons why they went for such a specific task is because it allows them to build an effective data engine to collect a lot of data. And so the way it works is basically in 3 stages. So the first stage is purely manual annotation. So we have actual people, we have an interactive tool to actually plot, the pixels that belong to different objects. And on this stage, we ask annotators to focus on objects that they are themselves confident in. And so the goal of this is to collect lots and lots of high confidence, high precision labels. Next stage is semi-automatic. So the goal of this stage is diversity. So now from the first stage, we already have our first iteration of model of SAM, of detector, and we can pre-fill some of the masks that we know with existing detector. And then what we do is we ask people to annotate some extra objects, just to basically now focus on the object that previously we didn't even think to annotate. And in addition, we can validate the quality of such annotation with object detector, because obviously knowing precise pixel segmentation of the object, you can just calculate the precise bounding box from that. And then the next step is now fully automatic. So now we have level 2 of detector that is trained on a lot of high quality diverse labels. And we do an extra step with some tricks to improve the quantity of the data. And the tricks are basically using automatic detection. So just have a picture and just scan it with different grid of points, or just use random points as prompts to generate some masks for segmentation. Then select confident and stable mask, and then also do stuff like non-maximum suppression and what's called usually test time augmentation, where you select different crops of the same image and try to predict the mask for the same point of that for different crops. And then you basically match that all together and see which detections seem to be the most accurate, the most correct, and that you add to your data. As a result, they collected a huge data set, so it is called SA1B. It has 11 million images and 1 billion masks. So just to give you a perspective, the COCO dataset that is typically used for object detection, that is typically used to compare different model, it only has like 100K images. The famous ImageNet data set that gave us ResNet, that gave us convolutions, that only has 1.2 million images. And SA1B, the SAM dataset, it's basically 10 times bigger than that, and it has a lot of masks. So we can see the plot here, where on the x-axis you have the number of masks per image. And we can see that SAM basically has lots and lots of pictures where we have a lot of masks. And so here's a really cool picture from the paper of what sort of images are there in the data set. And so we can see here that, yeah, some of them are fine, like they have like a bunch of objects. And then on some of them, there are literally hundreds, thousands of objects, and all of them are annotated. All of them have the actual predictions. All of the predictions seem to be quite on point, so they're of high quality. And so this is what we talk about when we talk about quality and diversity of the data. So if you were to go for something like fruit detection or fruit segmentation, suddenly you have a model that does that, and no other model did that before. So despite the fact that the task of promptable segmentation itself can be limiting, so just having SAM as a model, you wouldn't be able to detect bananas, for example, because you need to provide a prompt. But you can combine the model with other models to build upon that or to improve that. So one example might be to combine that to grounding dino. And so what we'll do is you would prompt grounding dino with text, please detect me some bananas, and then you'd use that box to feed that into SAM, and from there get the high quality pixel segmentation of the bananas that you have detected. So to reiterate, promptable segmentation is used here because it's easier to source data, it's easier to create a data set with a lot of diverse labels, and diverse in terms of classes that are there, so they are not limited to a specific set of classes that we have defined. It is diverse in the sense of the actual number of images we have there. It is not directly transferable to other tasks, so you would not be able to perform an actual instance segmentation and compete with other models on COCO dataset, for example. But you can do that with the help of an extra model. So one thing you can do is you can take maybe even low quality object detector and then actually improve that or build on top of that to go from object detection, bounding boxes to pixel segmentation. Okay, now let's look at the actual model architecture. So this is the actual picture from the paper. It looks quite similar to object detectors that we have seen before. So we start with an image. We pass that through image backbone. Here it's called encoder. In the paper itself, they use VIT transformer, although it can also be something like swing transformer or ResNet. And out of that, we get this flattened image embedding sequence. And then we have decoder. So the second input to the decoder is going to be this encoding of our prompt. I've actually seen examples of how that is done only with points and boxes. So it should be possible with text. They say it's experimental in the paper itself, where they basically use a side model called clip to generate these text embeddings. So this is not something we'll talk about today. Also, I've never really seen any mention or example of how to use that with a mask prompt. So we're going to talk only about points and box prompting and about this part as well. So first of all, how do we do encoding of our prompt? So again, prompt can be a bounding box, it can be a point. It can be both at once, although I don't think that makes much sense. And so what we do first is we pass these things through positional encoding. So for a point in the picture, you basically have 2 coordinates. For a bounding box, you have 4 coordinates. And then positional encoding is the thing that knows how to turn these into the actual embedding of size 256, for example. So the precise positional encoding used in SAM is called random positional encoding, which is a combination of statically initialized and sine cosine. So what it actually does is it first statically initializes half of the embedding vector, 128 coordinates, and then basically takes sine of that and cosine of that and concatenates them together. So it's a mix of random initialization and a trainable vector and actual sine cosine embedding that gives the model this opportunity of using simple math to compute relative coordinates. So both of these are fed as decoder input, and we also append 5 special tokens that by now are again just statically initialized trainable embeddings, but they will represent output of the model. So this is another moment that I think is quite interesting. So we can view the transformer, the decoder, as basically differentiable computer. And so here as an input, we put all different sources of information. So we can encode the bounding box, we can encode a point, or we can encode a question saying, please predict a mask, or please predict IoU confidence. And we put all of that in the input, and then decoder just sort of eats that, and it knows what to do with every token, and they sort of interact with each other, they interact with the picture, and then once we actually train that and we connect these outputs to the loss, then it starts to make sense. And this is how decoder looks like. So as one input, we have image pixel embeddings. So VIT transformer outputs 64 by 64 feature maps. So we flatten that and we get 4K 4096 sequence. And that is our first input. And second input is the query tokens. So 2 for the input, 5 for the output, 7 in total. So we always have exactly 7 tokens as decoder input in this model. So first what we do is self-attention between the queries. So we let them interact with each other, exchange information, and so on. And then we have 2 sets of cross-attentions. And so this cross-attention is actually pretty similar with what is happening in object detection models like Detector, but we have 2 of them. And so we not only update query representation, we also update image representation. So let's take this cross-attention as an example. So as usual, the self-attention or cross-attention in transformer takes 3 inputs, so query, key, and value. With the case of self-attention, all 3 of them are coming from the same sequence, and the output will obviously be of the same shape. In this case, we take key and value from the image, and so we have 4,000 sequence elements here. So we have 4K times 256 query key input, we have 4K times 256 value input, and then we take the queries as Q, right? So that's 7 times 256. So then what we do in normal attention, we compute attention weights by multiplying these dimensions to these dimensions. And so the common dimension will cancel out, And from there we get this 4k ins times 7 attention weight map. And then we take the value, right? And in this case, the value comes from image pixel embeddings again. And so we had this 4k times 7 attention weights map. We multiply it with this value, and now this 4k common dimension, it's getting crossed out. And so the output of this will be 7 times 256. So this dimensionality looks like the dimensionality of input queries. And so this is what we call it, despite the fact that this query here is basically weighted combination of this value input tokens. So this is how cross attention works. We've seen that in Decoder, so I hope that is no surprise to you. We can do a symmetric thing to do attention from image to queries now. So now we take queries from the image, we take key and value from these inputs, and we perform the same thing. So we compute attention, we compute weighted combination of values, and out we get this sequence with 4k times 256 dimensionality, and that is our improved image feature map. So if you look at this part, this is going to be exactly the same as object detector, Decoder. If you look at this part, it is symmetric to this part. We've also seen this precise method of image to query cross attention in grounding Dino, where we can basically merge information coming from the image with information coming from the text. I do believe that similar techniques are used in other image-to-text models like CLIP or ChatGPT, because basically this is a common mechanism where once we've projected different sorts of inputs like points, images, text into embedding, we can now basically perform attention between them, and it will just work. Since that was quite a lot of information, let me just repeat all of that once again. So in decoder attention, we have two sorts of inputs. So the one with 4k sequence length, that's the image. The one with 7 sequence length, that's the queries. So in self-attention, query to query, all of 3 attention inputs come from queries. So key, Q, and V. So we compute attention weights as key times Q. And that's going to be 7 by 256 times 7 by 256. So that's common matrix multiplication. What happens when we do that is we cancel out this last dimension. And so we get this 7 by 7 attention matrix, which says, well, what is the attention weight between every pair of queries that we had? Then we multiply that attention weights matrix by value. So we get 7 by 256 times 7 by 7. Again, the common dimension crosses out, which is now 7. And so as an output, we get this 7 times 256 output. And that happens to be the dimensions of our query input, so this is what we call it. Now, query to image cross attention, Q will be coming from the queries, key and value will be coming from the image. So when we compute attention weights, once again, we multiply key by Q. So we get 4k times 256 multiplied by 7 by 256. So now this 256 common dimension gets crossed out. We get 4k by 7 attention weights matrix. Now saying what is the weight between every pixel in the image and every token in the query input. To get the output, we again multiply value. So value is 4k by 256. We multiply it by our attention weights matrix. Now this 4k dimension crosses out and we get 7 by 256 out. So this query output we basically get as a weighted sum of this image embedding. And this is image to query cross attention. So we have Q coming from the image, key and value coming from queries. Attention weights are basically the same but transposed, so we still get this 7 by 4k attention weights matrix, which says the weight between every image pixel and every query token. And the output is value times this attention matrix. So the value now has dimension 7 by 256. And so the common dimension happens to this 7 in this case. And so we get the output of this long 4k sequence, which we say is an image sequence. So this is the output. So this time, this image sequence output we get as a weighted sum of query token inputs. And this is how we get the actual output. So out of the decoder, we get this updated version of our query tokens. We get updated version of our image feature map. So these two guys are not really used. Then we have 4 mask predictions, and each of them basically corresponds to unique prediction of an object, and we need several of them to distinguish between parts and subparts of the object. So for example, in our case, the point was somewhere here, and it might refer to the actual person, or it might refer only to his short, and so on. And so the mask prediction is basically a single embedding, 256-dimensional embedding, and the way to convert that to the actual segmentation pixel map is to compute dot product between that and the actual picture. So how it actually happens is we have our image representation from the decoder, we upscale it a little bit, so we upscale 64 by 64 up to 256 by 256, so we basically enlarge the picture. And to compute the dot product here, we need to downscale this embedding dimension, 256 down to 32. And then we compute the dot product between every pixel and this query token. And this dot product will yield one single number that is now saying basically the probability that this pixel belongs to this object. And so by multiplying to every pixel, you get this probability for every pixel belonging to this object. The final mask is computed as probability above a certain threshold. And this final 5th output is the IoU confidence. And that is basically an embedding that we then project to 4 numbers, where the first number corresponds to the confidence in the first image, second number corresponds to the confidence on the second mask predicted, and so on. So basically the task of this guy is to say, well, I know that this guy is going to detect some object segmentation mask, and the task of this guy is to say how precise it's going to be when compared to ground truth object. And obviously we need this extra confidence hat so that we can actually benchmark the confidence of our model, especially since it outputs 4 masks. So sometimes there is really no ambiguity, and in this case the model will output 1 really confident mask and then 3 random masks with 0 confidence, for example. And so this is our way of saying, let's filter out all the predictions with low confidence. The model uses the combination of 2 losses, so the generalized IoU and Dice loss. So IoU is intersection over union. So we refer to A as the ground truth object and B as the predicted segmentation mask. So the more they intersect, the better. So if IoU is 1, then that has to mean that they exactly match. Dice is quite similar, but here we can see that in the nominator we still have this intersection. In denominator we have just the sum of basically the area of 2 objects instead of union. Nevertheless, it works roughly the same. One thing that does mean is that, first of all, we need matching, right? So the model outputs some sort of object segmentation, and we need to match it to ground truth object segmentation somehow. So for that, we still use Hungarian matching laws, bipartite matching, the same as for object detection. Another thing that I find quite interesting here is how exactly do we propagate signal about precise pixel information? Because as you can see here, this loss basically measures how well our segmentation mask is, but it's not exactly telling us that, for example, if we have annotating this pixel as part of the object, there is no direct signal that, this pixel is wrong and this pixel is right. So I'll take a moment on explain how exactly this works. So first of all, let's go a little bit back and just look at other variants of how that might be done. So before this mask segmentation, one approach was to do pixel classification, basically, where for every pixel we just classify it as belonging to some sort of object. Now, obviously, this is harder if you need instance segmentation, because how do you exactly define like what is the sheep number 1 or sheep number 2? But it works for just classification. And in this case, the feedback that you give the model is really direct. So this pixel either belongs to the person or not. And if it is not, then you're just saying so. Like if the model is wrong, you're saying that you're wrong on this pixel. Another example is in object detection with bounding box prediction. So mean squared error loss actually looks at 4 coordinates of the bounding box. So x, y, height, and width. And it basically says that, the ground truth height is 100 pixels and you've predicted 95. So, adjust yourself. So this is pushing the predicted bounding box in the direction of the ground truth box, which is just what we need. With IoU, it's a bit more complex because now we have this complex function that depends on all 4 of these numbers. And so it's not really clear where the gradient of this loss will lead us. But we know that this IoU has maximum. We know that the maximum is when this predicted bounding box exactly corresponds to ground truth bounding box. And so if we have a smooth enough function, we know that the gradient will lead us to that. And actually, the IoU itself is not differentiable. So we use this analog called generalized IoU, which is smoother, which does let us go from point A to point B. And with mask loss like Dice or mask IoU, it's quite similar in that we have some predicted segmentation, we have ground truth segmentation, and let's say that predicted segmentation contains some pixels that are not really part of the object. So in this case, the loss is even less direct in that to define if a specific pixel is part of the object as predicted by this mask or not, we take this one embedding multiplied by the pixel embedding, and depending on that, we'll find out the truth. And the gradient with respect to this loss will basically say that, after this dot product, you had some features that matched some areas that weren't supposed to match. And so please do less of that and more of something else to do closer matching and improve your segmentation mask. So this is less direct. Nevertheless, we still know that, the perfect case is when they match exactly. And again, if the function is smooth enough, we can hope that the gradient will lead us to that maximum. Another interesting detail here is that the gradient will propagate both to this output token, saying which pixels to mask, as well as the image itself, the image feature map. And we will adjust both the sort of feature representation of each pixel and the output query token to do better match with respect to the pixels. Another interesting detail that I think is worth mentioning is this upscaling operation. So one way to do upscaling is just to do bilinear interpolation, which is basically enlarging the image, and you'd see it is a bit pixelated. So what is happening in SAM is using Transposed Convolution, which is a different beast on its own. So one way to visualize that is, first, if we remember what normal convolutions do. So we basically have this, let's say, 4x4 feature map. We apply some sort of kernel by sliding it along the image, and we get this downsampled 2x2 image. And we can sort of look at that as shining the light through the picture and getting this smaller feature map out of that. Transposed convolution, sometimes called deconvolution, is something in reverse. So we can actually sort of illustrate that as shining the light in reverse. So here we start with 2x2 image. We apply the kernel by, again, sliding it along, and we get this 4x4 picture out. And well, obviously 2x2 picture usually has less information than 4x4 picture, but in case when you also have embedding dimension, and you actually go from higher embedding dimension towards lower embedding dimension, which is the case for SAM, so then you basically have encoded a lot of useful stuff in these 256 dimensional embeddings, which do let you go down to 32 but increase your pixel resolution and actually have quite a high quality of the picture restored from that. And here's a brief demonstration of that which I did on my own, training a simple autoencoder on MNIST dataset. And here you can see results of such restoration after several epochs of training. So we start with something really random, then you get some good estimate of what a digit looks like, and then towards the end of the training, the restoration is almost perfect. So this 9 is almost, so this 9 is almost as good as this 9, for example. You can see some details are missing sometimes, but nevertheless, this autoencoder with transposed convolution does manage to do a pretty good job. And in this particular example, we first used convolutions to actually encode all the information in just one pixel. So we have 64 by 1 by 1 inner feature map, and then we expand that into 28 by 28, which is roughly 10 times more information. So we've compressed that with 10 times less digits, and we are able to restore the original picture using transformed convolution almost precisely. So a lot of the things actually deserve their own video, especially transposed convolution, for example. So I'm just going to leave the further reading links, and I'm hoping to do videos about that as well. So one thing to read about this mask level segmentation versus per pixel segmentation is Mask Former, which is mask segmentation with transformers, which talks a lot about both approaches, about pros and cons of them, and where we get these sort of mask level segmentation. Focal loss and dice loss used in segmentation. Conv transpose 2D, that's transposed convolution for upscaling. In addition, the datator model and deformable datator, apart from being object detectors, they're actually segmentation models as well. So even the original datator paper also talks about how to do instance segmentation, and they have the code for that as well. So it's also worth a read. Finally, let's talk about results. So as a primary result, they show this specific task that they were solving, so promptable segmentation point to mask. There's really not that many models that can do that as well. So they found the model called Rhythm that also does this. We don't really know how good that is, but it is basically, so SAM is extremely superior on a lot of data set, although like I, for example, haven't heard anything pretty much about any of them, maybe except Elvis and Cityscapes. So it's quite hard to compare zero-shot detectors, zero-shot segmenters, because it's hard to find some common benchmark that everyone is aware of. And so they have two numbers here. So one number is just for a single evaluation. And remember, the SAM model outputs several masks corresponding to parts of the object itself, the subpart. And depending on the data set, that's not actually what we want. And so in such a case, when you just want one mask and you select the mask with the most confidence, sometimes you actually get inferior results, like on this GTE8 dataset. But then if you swap that to a best out of 3, when you let SAM predict 3 masks, you compare which one is the best estimation of the object, and then select it, we can see that it now outperforms the previous state of the art on all of them, and just it's so much better in majority of the cases. Then if we compare that to something we know, so for example, Coco instance segmentation. So again, SAM cannot do instance segmentation on its own, so it needs to be prompted with something. And in the paper, they prompted that with VIT detector that outputs bounding boxes, used that as a prompt, converted that to segmentation masks, and they got 46.5 AP. And that's much worse than current state of the art. But then again, this SAM model haven't seen a single image from the actual Coco dataset. And a big part why you might lose so much quality is because every dataset actually has its own bias. So this is an example of the image from Coco dataset, where basically they didn't want to pay the cost of annotating everything. So you would see sometimes examples like these where you have a few hundred objects and most of them are not annotated because it was just too long to do. But think about what that does to the model. So you train the model to detect or segment sheep, and then the model sees this and actually gets penalized for that because the model thinks it's a sheep, but it's not annotated. So that's really not good for training. Seeing this, you understand why was it so important to have this data engine? Why was it so important to collect incredibly diverse data set where everything is annotated, so that you can actually train the model to know what is an object and what is not, without it having to basically adjust to this bias that you have in your own data set. Here's another example which is quite popular, where we use a combination of Grunning Dino, SAM, and Stable Diffusion to do something like this. So first we use Grunning Dino, we prompt it with something like detect me a car, and it outputs a bounding box. Then we feed that into SAM to get the actual pixel mask of this object. Then we just cut away that pixel mask, and then we ask Stable Diffusion to generate something on its place. So that's quite cool, I think. And this was it for today. I hope my explanations were useful. If there's still some questions, then stick around for the next video about reading the source code of SAM model, and see you soon.